Welcome back, students. In this lecture we'll see one more problem on how to draw inference line diagram for indeterminate beams. So let's start with an example. Directly we'll go on to the question. So make sure that you see the previous lecture before seeing this particular video. So here also in this question we have a two span bridge. It is indeterminate to 1 degree, right? And it is to be noted that both the span are having different I values. That maybe this span AD is twice the depth of or twice the width of the span EF, thereby the moment of inertia of span AD is twice the moment of inertia of span TF. But is to be noted that const E, the modulus of it as it is, remains the constant. Okay, so here in this question we have to find out the vertical ILD for vertical reactions of all the supports as well as the shear force and bending moment. Let's see, right? So what we will do is, in this problem the approach we will use is, first of all we'll find the ILD for dy, and once we have the ILD for dy, reaction at D, we'll try to relate other support reaction with ILD for reaction at D, and also we'll try to relate the bending moment at location C with the support reactions, right? So without any delay we'll start with finding the ILD for reaction at T. So it's well known that if you want to find out the ILD for reaction at T, what you have to do is you have to remove this particular support at T and release the structure so that you get a simple supported struck beam, and you have to apply unit load at every point and find out the corresponding reaction. So this can be done by removing the by force method, which is explained here. Okay, in other words you can use conjugate beam method also, and as per the Moeller-Bresler principle, all you need to do is remove this support, apply a unit load corresponding to dy corresponding to D, which is a unit load 1, find the deflection at each point. The deflection pattern will be something in this pattern. Find the deflection pattern at each points and divide the deflection at each point by the deflection at D. So this will give the ILD for reaction at D. So this is what we are going to do. So here you can see the supported D is removed and the release structure is a simply supported beam AD, and at B corresponding to the reaction at T I have applied a unit of 1, so I get a displacement pattern something like this and all. Now you have to find out the displacement at each point. So in order to do that, what we do is we'll draw the conjugate beam for this particular real beam. So the conjugate beam will remain the same, like it is simply supported, supports will remain as simply supported. Okay, and when you do apply this unit load, please note that the bending moment diagram for this particular case will be something like the reaction at this point will be downward, sorry, so you apply load at T, you'll get a bending moment. It's actually a triangle distribution, sorry, and when unit load is applied at T, the reactions would be 0.4 at E and 0.6 at F, which means that the bending moment value at the center is going to be 0.4 multiplied by 6, which is 2.4. So This is the moment diagram for the real beam. It's a triangle with a peak of 2.4. So when you have to load this with the conjugate beam, so you have to load the conjugate beam with M by EA diagram. So please note that for span AD, I is 2E, so 2.4 by 2 EI, which is becomes 1.2 area, and here it is 2.4 by EI only because for span DF the suction capacity is EA only. Okay, modulus of rigidity is EA, right? So this will be the loading for the conjugate beam. Now what you have to do is, with this loading pattern you have to find out the reaction, as well as if you want to know the deflection at each point, all you need to find is you have to find out the bending moment at these points corresponding in the conjugate beam. So if you want to find out the deflection at B, all you need to do is you have to find out the bending moment at B in the conjugate beam. If you want to find out the deflection at D, all you need to find is the bending moment at D in the conjugate beam. So with this given loading, you can use the moment sigma mx ma equal to 0, so you can find out what is the reaction here, and also you can use sum of what the vertical force is equal to 0. That way you can find the other reaction also. Ra plus Rf is going to be the total of this triangle, area of this triangle plus area of this triangle, and moment also you can find out as we see in the previous lectures, right? So straight away this is going to be the reaction values, and next step is you have to find out the deflection at each of the points in the real beam, say B, C, D, E, F, etc. Okay, so we'll move. So at the beginning you can see that for the real beam, which was this, the value of deflection at A and F is going to be 0 only. That's why I can directly write delta A and delta F is equal to 0, right? The next thing you have to do is you have to find out the deflection at B. So if you want to find out the deflection at B, you have to find out the bending moment at B, which is going to be minus 3.44 EI into 2 plus half into 0.4 by EI into 2, which is the area, multiplied by the lever arm to the centroid, which is 2 by 3, base by 3. So 2 by 3 u2, you get the value of deflection at B. Similarly, you can find the deflection at C, which is going to be minus 3.44 multiplied by 4, and then the area of the triangle, which is going to be half into 0.8 by EI into 4, and the lever arm is 4 by 3, the centroidal distance, right? So this is going to be 4 by 3. So find delta C also, you can find delta D. You can take moment about the left hand side of the D or the right hand side of the D. You will get the value as minus 13.44 by EI, and moment at bending moment at E, which is nothing but the deflection at E, it is going to be minus 4.96 into 2 plus area of this triangle, which is half into 2 into 12 by EI, which will be acting at a central distance of about 2 by 3 from E, right? So you multiply with 2 by 3, you get deflection ES minus 9.12 by EA. So that's it, we get the deflection values at each points corresponding to each of the points. So we'll tabulate that deflection values, and if you want to know the ILD value for dy, what you have to do is divide each of these deflection values by the deflection at D. So divide each of this value by this particular value, you'll get the ordinates of ILD for dy. So it is going to be something like this, and if you plot, you will get a ILD diagram looking something like this. Okay. now that you get the ILD diagram for dy, which looks like this, you can find other reactions which are other than redundant, which is ay and fy, by considering the equilibrium equation. Let's say that there is a unit load acting at a distance x away from A. So you can say that sigma ma equal to 0. So x into 1 minus dy into 6 minus 10 into fy is going to be 0. dy is already known for different values of x. So at different values of x, you can find out the fy also. So equation will be fy is equal to x minus 6 dy by 10. So each value of x, let's say for point A, the x value is 0 and the dy value is 0, which means that fy value is going to be 0. Let's say for point B, the x value is going to be 2 and the dy value is going to be 0.492. So if you substitute this, you'll get the value of fy as this much. So you can find the value of fy at other points also using this equation. So this will be the coordinates of ILD for fy. So if you plot that, you will get something like this plot. Okay, and we know that sum of the vertical forces should be 0, which means that ay plus dy plus fy should be equal to 1, which means that ay is equal to 1 minus dy minus fy. For each value of x, we already know that value of dy and fy. So ay coordinates are going to be 1 minus ordinates of dy minus ordinate of fy. So 1 minus 0 minus 0, this is going to be 1 minus 0.492 minus of 0.095, which is going to be something like 0.603. So likewise, you can find the other ordinates of ILD for ay at other points also, and if you plot that, you will get something like this. Okay, the next step is you have to shear force at C. So what you have to do is you have to draw a section at C and draw the equation for and derive the equation for shear force at C. So initially you can say that when the x was less than 4 meters, x is varying from 0 to 4 meters, you can say that on the left hand side you have both the forces ay as well as 1 kilonewton, which means that shear force is going to be ay minus 1, right? So this is written here. So from values x equal to 0 to 4, so that includes support A, B which is 2 meter and C which is 4 meter. For all this support, shear force value is going to be ay minus 1, which means that this minus ay minus 0, this minus 1, so it's going to be 0, this minus 1 is going to be 0.3, so 0.254 minus 1 is going to be minus 0.746. When the unit load crosses x, let's say the unit load is somewhere here, which means that unit load has already passed the point C, which means that if you now check the left hand side, you can find only one force, which is ay. So shear force is going to be nothing but same as ay when the x value is varying from 4 to 10, which includes value from C again, D, E and F. So which means that at C, D, E and F, the shear force value will be same as those values at of ay, which means that 0.254, 0, minus 0.72 and 0. So if you plot this, you can see that at C there are two values of shear force. So if you do the plotting, the ILD diagram will look something like this. Okay. So similarly, you can draw the bending moment diagram as well. So initially, you will consider that the unit load was on the left hand side of the C. So it is going to be bending moment at C is going to be ay into 4 is this distance minus 1 into 4 minus x. So this is going to be the bending moment equation for first case when x value is from 0 to 4. That is for points A, B, C, you have to use this particular equation. And for point, once the unit load crosses C, which means that the bending moment is going to be only ay into 4, because on the left hand side the unit load is no more there. So it's going to be ay into 4 only, which means that for the positions C, D, E and F, all you need to do is you have to multiply the ordinate of ay by 4. So ay we have, so if you multiply this by 4, you get 1.016. 0 multiplied by 4 is 0. 0 multiplied by 4 is minus 0.072 multiplied by 4, it is going to be minus 0.288. So if you get all the ordinates, you can plot that now, and you will get the ILD for bending moment at CS1. That's it for today's lecture. Thank you. I hope you will follow more examples and learn the method. Thank you.